So far, we've talked about sets, and then we've seen how to visualize them using Venn diagrams. We have talked about these three set operations, but we haven't had a ton of opportunity to work with them. We sort of identified what the intersection looked like in our last example, but let's play around with one that may feel a little more mathematical in nature instead of just grabbing like a set of months in the year. So anyway, so my universal set this time around is going to be, integers from 1 to 10 inclusive. So 1, 2, 3, 4, you get the idea. Again, the dot, dot, dot indicates a pattern that hopefully makes sense. And we'll call out a couple of subsets inside here. So A is the set 1, 3, 5, 7, 9. B is the set, let's say, 2, 3, 5, and 7. All right. So if you'd like, you can populate a Venn diagram exactly like we did with the months example, but let's just try to maneuver what the various like set operations would look like if we tried to combine these guys. So, well, first off, what if we just wanted the complement of A? So, remember that's everything that's in my universal set U that isn't in A. So you can think of it as kind of like, the opposite of this guy right here. And hopefully you can work out, that it's, we don't want 1, we need 2 because it's between these, then 4, and 6, 8, and 10. So that's what our complement looks like. You could do the same thing for B. You'd have what, 1, then 4, and then what? As you say, 1, 4, 6, 8, 9, 10. So you could work it out, same way. So if we wanted the intersection of A and B, A intersect B, remember, that's what lives in both sets at the same time. So if we look at these guys here, well, what do they have in common? Well, 1 only shows up at A, so it's not part of the intersection. 3, 5, and 7, well, they all appear down here, but we don't have 9, so we need 3, 5, and 7. We don't need either of those two, and 2 doesn't show up in A. So our intersection in this case is just 3, 5, and 7. So lastly, what about the union of these two sets? So now remember, you can think of this as kind of just taking the two sets and mashing them together. Now remember, we wouldn't repeat elements, so if something shows up twice, we don't write it twice. So what I'll often do is I'll just kind of take whatever comes first. So in this instance, I'm just going to list everything that's in A. And then add in anything that I don't already have taken care of that comes out of the second set B, which in this instance is simply the number 2. Now, if you'd like, you can rearrange this if it bothers you to have the number 2 hovering around in the back. I get it. So it's perfectly fine if you want to rewrite this as 1, 2, 3, 5, 7, 9. That's perfectly hunky-dory. All right, so those are the base operations. Sometimes we actually need to deal with more than one operation at once, though, so bear with me for just a sec. Let me clear some space. All right, sort of a question you might end up having is, well, what if something like this comes up? A union with B complement. So does that mean that I want, like, do I do the complement first or do I do the union first? How do I go about this? Should I work out the union and then do the complement or vice versa? As it turns out, there's sort of an order of operations as far as set theory is concerned, which you may remember a similar kind of order of operations when you deal with like plus minus, multiplication, division, that kind of thing. So say hi to Aunt Sally for me. Anyway, so as it turns out in this instance, if you don't have any kind of parentheses grouping things up, you do complements first, then apply any unions or intersections. So we actually need that complement of B that I mentioned earlier, which was 1, 4, 6, 8, 9, 10, I think. 1, 2, 3. Yeah. So now I form the union of A with this stuff, and if you follow along like I suggested previously, we already have 1, 3, 5, 7, and 9. What are we missing? Well, now we add We have to add in 4, 6, 8, 10. And again, if you wanted to rearrange this so they're in order, that's perfectly fine. Go ahead, have at it. So what's this about parentheses? I'm glad you asked, rhetorical student. So in this instance, just like when you were doing regular arithmetic, if something's inside parentheses, you need to deal with it first. This means we do work out A union B first, and then take the complement of what comes afterwards. So it's always felt weird to me when I write this. So we have, I don't like putting the complement thing just by itself outside the curly braces, but I don't think it matters. All right. So yeah, I did take the liberty of writing the 2 in order. I'm one of those people that it kind of bothers, but anyway. So now I need everything that's not in here, because this is a complement. We want everything that is in U that we haven't already accounted for. So if I look at this, say I've got 1, 2, 3, I don't have 4, 5, 6, 7, go to 8, then we have 10. So needless to say, different looking object. Before we had like everything but 2, right? Now we've got, just 4 numbers instead of like 9 of them. So yeah, there's a pretty substantial difference there. All right, so I want to take a look at one more real quick. All right, so now we've got a complement sitting on each thing. And again, our order of operations says we need to deal with the complements first, then we apply this intersection symbol that's living in between them. So let's see, we said before that was already a complement. Then we want to form the intersection of that guy with the complement of B. So 1, 4, 9, 10. All right, and so now we kind of look at this and say, well, what do we have in common? Well, we don't have a 2 in this one, so he's out. 4, 6, 8, and 10. Yeah, all 4 of those show up, but we don't have this 1 or 9. So, So yeah, we get that. Does that look familiar? Feels familiar. So yeah, this was what we just came up with when we did the A union B and then took the complement of what we got out of a union, right? That's a weird little coincidence. Or is it? You probably already know the answer. All right. So I did want to take a look at sort of one more tweak to this notion of how we deal with sets and set operations. What if we end up adding another set to this thing, a different subset besides A and B? Okay. So now I've got a set C right here. If you were doing this like visually by populating a Venn diagram, in terms of drawing in a third set, it's kind of important to make sure you know how to arrange these. So here's what our 2-set Venn diagram looks like. For a third set, we need to make sure that in general it overlaps both of our previous circles, so don't just kind of bolt it onto the one side here. I usually draw it kind of down here. Some folks you could technically put it up top as well, potato, but conceptually, then you can sort of populate this the same way we have in the past, like figure out, well, what lives in here? Well, that's what would be in all 3 sets simultaneously. So looking at this, that's just what, 3 and 5 are the only things that pop up in all 3 of these, and you could sort of fill in the gaps, from there. All right, so same deal though. What if we were wanting? Actually, here I'll make this a little more. What if we wanted B union C complement? Okay, so we see the parentheses there, so yeah, we need to apply those. We do the union first because we do what's in the parentheses first. So we have complement of 2, 3, 5, 7, 1, 8. When we add on the extra stuff that we pick up out of C in this instance, and we get that guy right there. Now, last thing, now what do we not have? Well, we've accounted for 1, 2, 3. We don't have 4. We don't have 6. We've got 7, 8, 9, 10. So this time around, that's the set we'd end up having to work with. Okay, so like I said, you can play around with more of these set operations and see how they end up interacting. But I wanted to wrap up this video by taking a look at a formula that ends up coming up in some of the homework problems and comes in handy when you're dealing with, say, bigger sets. So if sets turn out to be really big, like populating out a Venn diagram for them could be, kind of a pain, right? So what will often happen is when sets get bigger, you stop focusing on the individual elements and then focus in bigger picture terms like talking about cardinalities, that sort of thing. So as it turns out, there's a kind of neat formula that ends up, giving you a way to calculate the cardinality of a union of a pair of sets. Again, remember that n represents cardinality. It's not n times alpha. Anyway, so what you might end up trying to do at first is just add, the cardinalities of A and B together. That, makes sense, but the problem is there's some stuff that's getting double counted. Anything that's in both A and B is getting counted twice. And what's in both A and B is the intersection, as we've talked about before. So the formula ends up looking like this. N of A plus N of B minus N of the intersection. So for what it's worth, I did this with a group of students at one point. I had them give me some demographic data. So these were actually cardinalities from a previous Math 107 class. So one group had 11 people in it, another group had 19, and then it turned out that there was a substantial overlap. That of the 11 that were in set A, 10 of them were also in B. So if I wanted to figure out, how many people, in this particular class fell under either of the two headings, like a union, then I'd have 11 plus 19 minus 10. This was particularly important because, if you just added those two numbers together, you get 30, and that was more than I had in the class, which should feel weird. So as it turns out, you work out the arithmetic there, and there were 20 people. So for what it's worth, I think it was, native to North Carolina and first-year students or something with the two groups. So I had only 4 or 5 people who were neither a first-year student nor a North Carolina native. So this is actually kind of a good transition point because wrapping up section 2.1, where we end up going is what can we do? What does this set theory Venn diagram stuff actually do for us? Where would we use it when we're not in a math classroom? It's an excellent question, and that's where we're going to be headed next.